Hey, what's up, everyone? It's Miss Wesley. It is pre-calc time yet again, and today we've got something exciting planned. We get to start on unit where we are going to learn a new way of graphing. And I know we love graphing on the Cartesian plane, rectangularly in terms of x and y, and it was okay graphing sequentially and parametrically, but this is the class of many modes, so we're going to embark upon polar graphing today. And I wonder what you think of when you just hear polar graphing. Does it make you think of polar bears or the North Pole, perhaps? And there is a reason why they call it polar graphing. Check out this grid here for the graph paper for the warm up. I'm looking at the front of a new packet, a polar packet on page 1, where we'll look at some examples together today. But the warm up says to plot the points. A is 2, -3, and then B is -4, 5. So I'm just plotting these regularly, right, as an x comma a y. One of them lands down in quadrant 4 and the other falls up in quadrant 2. Now before I get too ahead of myself and I flip this around on you, we got to pause for a joke. So the joke is, it's actually a gift to you. It's a joke you can use on your friends. You tell them, do you have a knock knock joke you could tell me? And let them like fight you on it. No, I don't want to do this. I don't have a knock knock joke. But when they think of one, they say, fine, knock knock. And you say, instead of saying who's there, you say, come on in, the door's open. And then they never get to tell their joke. And that's the joke. So what could be new about plotting just these plain old points on here on page 1, B and A? Well, if we're graphing rectangularly, we're using an x and a y coordinate in each case, an x and a y. Today with polar graphing, we're going to assign points polar coordinates. I'm skipping down to this middle blank, and they're going to be r comma theta. And I wonder if you recall what an r might stand for. And I know theta we've seen a lot. We've used it in trigonometry to designate an angle measure, right? And an r should stand for radius. So I could actually estimate polar coordinates for A that would land you right in that same exact spot, 2 comma -3. You're going out a certain radius, a certain number of rings. So 1, 2, 3, in between the third and fourth ring, maybe at about 3.5 radii out from the pole, from the center. What angle are you going? Well, you're going all the way in between those two lines. The angle's it's a quadrant 4 angle. I'm just going to estimate it because we're just eyeballing things. Maybe like 310 degrees would land you if you came out that many rings and you went over from 0 degrees or radians over about 310. That should land you where A is. Let's see if we could try the same thing for B. We're just estimating here. About what radius would you be coming out? Well, you're going out 1, 2, 3, 4, 5. I think just past 6 rings out to get to point B. So maybe I'll call it like, I don't know, 6.2 or 6.3. And then what angle are you coming up? Well, you're in a quadrant 2 angle here. Let me try to see if I could just at least draw a little line. And I'm just going to pick some estimate here. You're going up about, let's say, I don't know, 130 degrees. So we will not be playing the guessing game this entire packet. We're going to learn conversions that are going to be useful between polar and rectangular coordinates and graphs. I am not just teaching you this for fun and just because, oh, it's just fun to learn another way to graph. I'm teaching you this because there are some really cool designs that you can graph polarly and cool relationships between r and theta that you can express a little bit easier in this version than you can in a rectangular form with x and y. So to form the polar coordinate system in the plane, you fix a point O called the pole. And O stands for origin. It's right at the origin in our case when we're graphing. And we're going to construct an initial, let's show this, an initial ray. Here's the ray here called the polar axis. It's making me think of Polar Express over here. Good memories. Then each point P in the plane can be assigned polar coordinates, r comma theta, where r we're going to call the directed distance from the origin or from the pole to the point P. So this distance here, and it's directed, is going to be r. Directed meaning r could actually be positive or negative. That's a spoiler for what we do next. Theta is going to be a directed angle, measured the normal way, counterclockwise from the polar axis to the segment OP there. So you go out up the angle theta, you come out a certain amount of radii here. And just to give ourselves a little bit of extra vocab, because I want you to be covered for no matter what the directions look like on any given example, rectangular coordinates have two synonyms. Rectangular could also be known as Cartesian, little ode to our friend, French philosopher Rene Descartes. They could also be called standard coordinates, standard form. Any of those are going to mean that you're plotting in terms of an x and a y. X comma y are coordinates that are rectangular, Cartesian, or standard. Polar, I can only think of two names for polar coordinates. We're going to call them polar coordinates. That's what the packet is called, for goodness sake. So polar coordinates, in the book, you'll sometimes see polar coordinates referred to as trigonometric coordinates, and they will be known as a radius, comma, a central angle, theta. Okay, keep all this in mind. Now, like I said, the fun part begins. It says examples. We have a huge circle here. I gotta hide because I'm always blocking part of it. Where can I go? It says to plot each point from A down through H, and they're given in polar coordinates. So what that means is each time you see like a 4 comma 30 degrees, you're given a radius and you're given a central angle theta. Now, because there are so many of these to plot, and because this is really good trig review, can you give yourself your quadrantal angles labeled on the four kind of north, south, east, and west of this grid? Because now we're graphing on circles instead of graphing on a Cartesian coordinate plane like we're so used to. Here's 0 degrees or 0 radians. I think what I want to do is label this up all in radians. It's good practice for us, and I just kind of prefer radians to degrees on this picture, regardless of whether your point is given in degrees. So 0, up here you've got this next quadrantal, pi over 2, pi, and then 3 pi over 2. Boy, did I miss this stuff. And if you came full circle, pun intended, you'd be back at 2 pi. Now, there's no reason to label every single line on this picture. I don't think we need to at this moment, but why don't we just divide the pi up into a few more pieces? You'll notice from 0 to pi over 2, there's 1, 2, 3, 4, 5 different partitions, partitioning off 6 sections. So a sixth of half pi is going to represent each line. And we'll say here you have, if you're going from here all the way to pi, this is pi over 6, this is pi over 4, and this one's going to be pi over 3. In other words, you have 0 degrees, 30, 45, 60 degrees, your special angles in quadrant 1. And then, I don't know, just to label a tiny bit more, I said we wouldn't go all out. I just want to go to each other quadrant and label the quarter pies, just so that I have a little bit of a bearing around all 4 quadrants. Your 0, pi over 4, 1 quarter, 2 quarters. Here, if you skip a few lines, you get to 3 quarters pi, 3 pi over 4. I'll leave the rest of the labeling. If we need to do it later, we can. Here's 4 quarters pi, skip a couple lines, 5 pi over 4. Here's 6 pi over 4, that's already labeled, quadrantal, skip a couple lines, 7 pi over 4, and then you're back to 2 pi. All right, I'm dying to graph these things. Let's label point A. You're gonna come out, what I like to do is I do this out of order. I know R is listed first, but I like to go to theta first. First, I find 30 degrees, figure out what line I'm gonna fall on, then I come out a certain amount of circles. Go to 30 degrees, that's also known as pi over 6. Where are you gonna put point A on this line? Well, here goes nothing. We're gonna graph it out 1, 2, 3, 4 circles. Radius was 4. So I'll label point A right at that intersection of that ring with the line. Okay, let's do the next one. Point B, we can check off A. 2 comma 5 pi over 6. Okay, so we had labeled these things in radians, but we didn't quite get to 5 pi over 6, so let's find it. What quadrant is that in? Well, it's not quite pi. It's 1/6 less than that. It's going to be here somewhere along this line, 5 pi over 6. 5 pi over 6, we need to come out 2 rings or 2 radii. So go up from the pole, come this way towards 5 pi over 6, 1, 2 circles out. And we'll put a point B. That's going to fall in quadrant 2. Remember, each time we label one of these points, it's not like we had to do this polarly. There are also rectangular coordinates for A, and there are rectangular coordinates that exist for B. But I'm getting ahead of myself. We'll get to those conversions later. Let's look at C. Positive radius, negative angle measure. We can handle it. Let's find theta first. Where would negative 15 degrees fall? So start at 0. I'm going to go 15 degrees in the clockwise direction, this way. somewhere along this line at negative 15, I'm 3 circles out. 1, 2, 3, and then we'll put a C right there. All right, are we having fun yet? I hope so. Next one, D. Oof, star this one. Okay, so a couple of these, D, E, G, and H, are going to have a negative radius value. We are not used to that. We are used to a radius being a positive distance from anywhere on the circle to the center of the circle. Well, you know what? This is a directed distance in this unit. So if R is positive, you're going to go that way, right, on the positive angle measure. If R is negative, watch what happens. We do a little flipperoo. So start with 5 pi over 4. Can we find that first? Figure out the angle. So 5/4 pi, I think we have it labeled down here in quadrant 3. Now, I'm wondering if you can guess what I'm about to do next. Right now we're focused on this line here, 5 pi over 4, but that's only half the line. The line extends up into quadrant 1, and that's the ticket. For a negative radius, you're actually going to flip-flop over to the other side of the line. So I was at 5 pi over 4. I'm going to go over to the line pi over 4, and I'm going to come out 2 rings because it says negative 2. So the negative means we flip over, the 2 means we go up 1, 2, and what do you know? Point D actually lands up in quadrant 1. Okay, pretty good, pretty good. How about E? Negative radius again, that's okay, we can handle it. Let's find this angle first, 150 degrees. Think of a quadrant, think of where that will fall. Well, 150 degrees falls in quadrant 2. It is also known as 5 pi over 6. We already have point B on this line, but because the radius is negative again, we're going to flip-flop to the other side. We actually don't have enough circles on this picture to fully graph this, so we're going to make room for it. So we're going to come out, where were we? 5 pi over 6. It gets a little tricky by the pole there. We have to flip over to this line here, and we're going to come out 1, 2, 3, 4, and imagine there's a 5th circle, and we'll label that point, what letter was it? E, we'll say, is way out here. So we've extended, kind of flip-flop from 150 all the way over to 330, and E is going to fall a little out in space here in quadrant 4. Okay, couple, 3 more left. So it says pi over 2, 2.5. We can handle a decimal radius. Let's see, pi over 2, that's going to be up 90 degrees along this line. Instead of coming out a whole number of circles, can you estimate? Come out 2.5. So 1, 2.5 for the radius gives me point F, which is quadrantal, right on the 90-degree line. How about G? G is both negative for these last 2. So you still find the angle first. That's a good strategy. Go negative 30 degrees. So I'm going negative 30, so 1530. I'm on this line here. And then you're coming out a negative amount of rings. So we'll go to the other side, flip-flop to 5 pi over 6, and we'll come out 1, 2, 3 circles. G should be over in quadrant 3. Pretty cool. And the last but not least is H. We are at negative 2 pi over 3, so start at 0. You want to go 2/3 pi clockwise this way. So 1 pi over 3 would be here. 2 pi over 3 would be down here. This is also known as, we could call this 4 pi over 3. That is also negative 2 pi over 3. So 4 pi over 3 is the line we want to be on, but not for long because we want to flip-flop over and go 4 rings up. So flip-flop yourself across the pole up to the line pi over 3. And we're actually, where I drew the arrows where I want to be. I want to come out 1, 2, 3, 4 circles to label point A. And before moving on to any other example, I do want to take this opportunity to point something out. We just practiced plotting a bunch of points in polar coordinates. Well, couldn't you make the argument, let's take this point H that we just got finished plotting. You had these negative r and theta values, but you ended up landing in quadrant 1. Shouldn't there be other equivalent ways to name that point with polar coordinates? Absolutely. I bet you could guess a few. Couldn't you just go to pi over 4? Like the spot where it lands, or I'm sorry, I should have said pi over 3, right? It lands at pi over 3. And then come out 4 radii, 4 circles. I mean, this should be an equivalent way to name the exact same point. It doesn't have to stop there. If for some reason you wanted to use a negative angle, think of the angle that gets you all the way from 0 to that line. Negative 5 pi over 3 would do the trick. So keep all this in mind. These angles are periodic, they're cyclical around the unit circle. So there's going to be multiple ways to name points and cool ways to convert back and forth between polar and rectangular. Talk to you soon.